start with the first talk by Alexander Turbiner, which is going to talk about quantum and harmonic oscillator solution. Okay.
First of all, thank you very much for a chance to talk here. And I should start with congratulations to the Vilker. I want to inform you that the 60 is not a critical point. It's not transition point. Life continues, so please continue. I apologize that I didn't recognize you since we met with Vilker more than 30 years ago in ETH in Hunkenberg. But that time, Vilker had a lot of hairs, and therefore it's very difficult with time to recognize. I will talk about the oldest problem of quantum mechanics. When Schrödinger, I emphasize even in absence of Jörg Fröhlich, that Schrödinger wrote this equation, which carries his name, not von Neumann. And the first problem which Schrödinger, after this equation was written, was tackled, was one-dimensional anharmonic oscillator. And who tackled this problem? Guy who was definitely associated with ETH in Zurich, and that time in Zurich, not in Hunkenberg, Wolfgang Pauli. I still don't know how to pronounce. In Russian, we're saying Pauli. But Germans told Pauli. Pauli, okay. And actually he considered not only anharmonic oscillator, he considered two fundamental problems of quantum mechanics. It's hydrogen atom in constant electric field and hydrogen atom in constant magnetic field, which about the person from Denmark made in the first day, I would say, remarkable talk. I will mention his name since, at least to me, this is my particular profession, this physics in magnetic fields. I was pretty impressed by his talk, and perhaps for this reason I asked a number of questions. But coming back to Pauli, that he had very strong personality, and I would say that many people from ETH had strong or extremely strong personality. One of them gave a talk yesterday, being the first. And Pauli was personal friend of Landau, of Lev Landau, famous Lev Landau, and therefore certain things about those three problems I mentioned, I know in folklore, since I belong to Landau school and all my teachers were direct Landau disciples. Therefore, in folklore, I knew that Pauli was the first, but he didn't publish anything. This was part of his likely personality, I don't know. So let me start with introduction, with motivation. So classical anharmonic oscillator, by definition, it's a system, one-dimensional system, where the Hooke restoring force is linear or nonlinear. This Hooke force is written here, and if all those parameters equal to 0 and we have linear force, this is really equivalent to harmonic oscillator if we will restore Hamiltonian or Lagrangian. And of course, description of this classical anharmonic oscillator related to the theory of nonlinear vibrations, periodic motion with large amplitudes, which is important, and correspondingly for mathematicians with Jacobi elliptic functions. And Jacobi, in order to solve this problem with very simple anharmonicity, those terms beyond of linear, quadratic, and cubic are called anharmonicity. He introduced elliptic function which carry his name, Jacobi elliptic function. So the natural question is, what about the quantum theory of nonlinear vibrations? And this is exactly the problem of anharmonic oscillator. The Schrödinger equation is written in a very standard and simple way. So we study its spectral problem for Hamiltonian, and Hamiltonian is defined here. Potential is written in a little bit unusual way, but this is equivalent to the standard things. And the potential, what appears here, has a following form. So it's type of Taylor expansion. Usually we consider Taylor expansion up to a certain finite order, and G, what appears here and which is going to play a very important role in this presentation, is called coupling constant, following physics nomenclature. H bar here, it's Planck's constant. M is mass of the particle. And parameters, what appears here, A1, A2, etc., they're called parameters of anharmonicity. And if coupling constant G goes to 0, we arrive to harmonic oscillator potential. Well, that's it. Next. How the differential equation looks like? Extremely simple and very attractive. It's just for the case of quartic oscillator. So attractive and so simple that thousands of papers published about this differential equation. Thousands, I emphasize this, since 1926. But the question is that what we can say about the situation when the coupling constant G is large, is non-zero, is large, and so as I mentioned, thousands of papers published, and if you read carefully those papers, there is a certain very clear conclusion. Don't even try, no hope. So all those papers, they picked up some pieces, but to imagine that one can write explicit solution, whatever solution, no hope. So it's clear that new ideas needed, new understanding of the situation and new approach. Let me mention those new approaches. First of all, it's very important the understanding that this problem cannot be solved exactly in terms of elementary functions, higher transcendental functions, or elliptic functions. It's definitely something beyond of our present knowledge. So we can hope only to some type of approximate solution. Believe me, this was type of breakthrough understanding. People hoped very much that we can really find some solution in closed analytic form. So our goal is uniform approximation of eigenfunction. Then the problem, next understanding is that we will focus on the problem in real domain only. Real coordinate space, no complexities, real potential, real coupling constant, real anharmonic constant. Motivation, physics motivation, we live in the real world. Complex numbers, it's our invention of human being beyond of this real world. So analytic structures in complex space should be ignored. And the question is, can we ignore them? We don't know, but we can address to this question later on, if we will succeed to get solution. The third point of understanding would be that Schrödinger equation is not adequate object to study, much more adequate to study Riccati equation. So we consider nonlinear spectral problem instead of Schrödinger equation, which is linear spectral problem. So this is the famous Riccati equation. I will talk about this. And this Riccati equation, which in somehow physics was written by Bloch, not Riccati, or revised by Bloch. And the y, what appears here, it's a famous function which is called logarithmic derivative of wave function. So we just take Schrödinger equation, substitute, and arrive to this equation. And we can immediately recognize that there is a problem, mathematical problem with this equation. The h bar is in front of the highest derivative. What does it mean mathematically? Bifurcation for h bar equals to 0. Conclusion, don't go to h bar equals to 0. H bar should be placed 1, or just a physically measured value, whatever it is. Don't vary h bar. The fourth component is that surprisingly, the problem I mentioned is not three-parametric problem. It depends only on single parameter. And this single parameter is presented here. It's so-called effective coupling constant. So it's made out of Planck constant, mass, and coupling constant. Single parametric differential equation, which is already great observation. And the energy is measured in so-called atomic units, but those atomic units just really, energy has dimension of this guy, what's presented here, which is square root of h bar squared over 2m. And this should be, since it's dimensional, it's taken away from energy. And the energy, what appears here, it's dimensionless. So, which is good, since we don't deal anymore with dimensions. So the next conclusion that h bar dependence should be hidden, just to avoid temptation, which unfortunately very much was spread in mathematics and physics communities, saying semi-classical limit, its h bar goes to 0. It's wrong. It's not h bar goes to 0. Semi-classical limit is when the action on corresponding trajectory is large or goes to infinity. So h bar should be hidden. So to hide this h bar dependence, we will write two new equations, one which is called Riccati-Bloch equation, and another it's generalized Bloch equation. And those equations are written in very unusual coordinate space. So the first equation is written in the coordinate space, which is square root of h bar minus 1 multiplied by x. And in other coordinate spaces, so this is simply trivial change of variables, it's gx. And then assuming, this is another idea, assuming smoothness of logarithmic derivative, y, what I wrote y, we will try to realize the simplest possible idea. We will try to match two asymptotic expansions at small x and large x to a single function. So we play with matching. Now several names associated with this problem, which made a very important decisive contribution, in particular from my personal perspective. I mentioned first was Wolfgang Pauli, 1926, perturbation theory, and he was the first who calculated first corrections in perturbation theory for anharmonic oscillators. Then it was Freeman Dyson, 1957, who understood that the perturbation theory is divergent, has zero radius of convergence. And this is very serious deficiency. Then remarkable paper by Carl Bender and T.T. Wu, 1969. They, in contemporary understanding, they developed so-called theory of weak coupling, and in particular, they discovered analytic structures which nobody before then was could not imagine. They called it Horn structure of singularities in coupling constant G. I will show the plot. Then Lev Lipatov, 1977, he discovered the connection of quartic anharmonic oscillator to lambda phi to the 4 quantum field theory. Then somehow my contribution appeared as a nonlinear realization method. This means that we should really not deal with Schrödinger equation, we should deal with Riccati equation and study Riccati equation. Then in 88, somehow the theory of strong coupling means G goes to infinity, was developed, and incredible phenomena of duality was discovered. I will talk about this. And in 2005 and 2010, there were two attempts to write intuitive solution, intuitively present approximation, uniform approximation of ground state wave function. It was pure intuition, no explanations. But then in this period, 2018-22, this generalized Bloch equation was derived and path integral formulation was used, and it was shown that perturbation theory in this generalized Bloch equation is really nothing but loop expansion of path integral corresponding to anharmonic oscillator. And then Juan Carlos del Valle, who is present here, been enthusiastic young PhD student, and we attacked this problem and solved it. And solution led to my understanding, very surprising result, that we found this solution in 2021 and published paper in Journal of Physics A. Journal of Physics says that Times was still very good journal in mathematical physics, maybe the best journal. 5 referees, all positive. Surprising result. But in 2023, we published a book in World Scientific exactly about this. And up to date, surprisingly, those two pieces of work, original article and the book, collected over 1,100 readings and a certain number of citations, but not many. Okay, now the main body of the talk is quartic symmetric anharmonic oscillator. So quartic symmetric single well anharmonic oscillator, the simplest non-solvable exactly, or non-solvable in whatever sense, and the most studied problem in one-dimensional quantum mechanics. Potential has 3 equivalent forms. This is standard form I mentioned. We can take x squared away and to write this part. Or we can write this in such a form. All 3 forms are important for understanding of the problem. As I mentioned, over 1,000 papers published since 26 about exactly this potential. My original personal motivation when I was just a young PhD student, I never been PhD student, but after graduation in university, my personal motivation of this was 0-dimensional lambda phi to the 4 quantum field theory. So 0 plus 1 space-time. This means we will study this problem from this perspective. Okay. So weak coupling regime. So weak coupling regime, this means that G squared goes to 0, and for simplicity, we put H bar equals to 1, and mass we put equals to 1/2. So the first observation was, I call it, joke of the nature. If you will try to develop perturbation theory for ground state, or for any really state, in powers of the coupling constant, it's pure algebraic procedure. Means that all coefficients in perturbation theory for eigenvalue and for eigenfunctions are rational numbers. And this joke caused a lot of efforts to people, since people thought that if we have rational numbers and infinitely many rational numbers, this means that the original problem is of algebraic nature. It's natural logics. And also, there is another observation that the zero radius of convergence of perturbation theory. This was type of the cold shower. This means that coefficients in perturbation theory for eigenvalue, for any eigenvalue in powers of G squared, grows factorially. Each eigenvalue has infinitely many square root branch points in complex G squared plane. Meaning of those branch points, levels crossing. Barry Simon dedicated his PhD thesis to study this phenomenon in particular, and did not succeed much. And success to understand this structure came 50 years after, due to two pure mathematicians. One is Gabrielov and Yeremenko. This is Purdue University. One, Yeremenko, is the great expert in topology and former disciple of Israel Moiseyevich Gelfand. And Yeremenko is the greatest really expert in ODE. Only in combination of those two knowledge, of those two expertise, they were able to prove that the ground state, that there are two infinitely sheeted Riemann surfaces of eigenvalues, and each sheet is characterized by ramification points, infinitely many of those square root branch points. They were unable to prove that the branch points, this is square root branch points, but they proved that they are algebraic points. But from physics point of view, it's clear that this is square root branch points. And the meaning of this square root branch point is that if we will take ground state energy and consider analytic continuation of ground state energy to the complex plane m squared. M squared is just defined here. It's the 1 over g in power 2/3 in coupling constant. There will be such an infinite set of singularities. They are accumulated to infinity. And this is Bender and Wu. And why it's called horn structure, it's also clear, since you can see the form of the horn. And the meaning of those points, that if we will start, for example, from this point and go around these square root branch points and return, we will come to second excited state. But if we will take the path from here to point number n here and return, we will discover that we arrived to the 2n shade, which correspond to the 2nth eigenvalue. What was not clear at that time, but it's clear now today, that this structure of singularities, similar structure, it's general for any potential with perturbation. there exists such a type of structure. They can be different, of different form, but again, for enharmonic oscillator, quartic, which is simplest problem, this type of singularity exists. And Bender and Wu, who discovered this, they just were able, using true semi-classical expansion, calculate how those points goes to infinity, and the positions of those singularities go to large n to infinity. So those 3 points I mentioned, this, and this is just due to Bender and Wu, 1969. And let me mention that the Carl Bender, when he did this work, he was PhD student in Harvard. And he got immediately after publication of this work, immediately he got a tenure track position without being as a postdoc at MIT. And in 27 years old, he became the youngest full professor in physics in the US history. But then Italian contribution was that there are no exponentially small terms if you will study perturbation theory. So perturbation theory for the ground state or for any excited state is given by Taylor expansion in coupling constant G. There is no trans-series I mentioned in the very first day. Okay, and as I mentioned, surprisingly, all those coefficients here, and this is expansion for wave function, they were Fn polynomials with rational coefficients and all An rational numbers. They are very nice, appears very nicely. They cannot be classified since they are some sequence of beautiful rational numbers, but always in denominator, the denominator of those rational numbers is just 2 in some power. Remarkable general observation. Okay, now, strong coupling regime, G goes to infinity, so perturbation theory in powers of these inverse powers of G. This is to calculate coefficients of this expansion. This is non-algebraic procedure. It's extremely difficult to construct this expansion. Radius of, this is convergent expansion, radius of convergency of order 1, but there are no estimates of this radius even today. Nobody knows how this convergency appears. First 9 coefficients were calculated by, due to us, 1988, and then Vinegar in 96, and he published paper in PhysRev Letters due to the importance of those coefficients. Since the people had hope that once we study convergent perturbation theory, we can just really solve the problem. Then the duality was discovered that coefficients B, what appears here, can be represented as infinite convergent sums of coefficients A. So this, and vice versa, this means that weak coupling and strong coupling regimes are connected. Who could imagine this? Okay, now I proceed to the main body. Okay. I understand that I have 20 minutes, so the talk lasts 50 minutes, so I have 20 minutes. So first of all, how to go from Schrödinger equation to Riccati equation is standard procedure. So we take exponential representation of a function, h bar is here in denominator, substitute to Schrödinger equation, mass equals to 1/2 for simplicity. We arrive to this remarkably nice looking Riccati equation. The coupling constant G squared appears here, and as I mentioned, h bar appears in front of the first highest derivative of this nonlinear equation. But then, so this is nonlinear. This is, let me emphasize, this is nonlinear spectral problem. So you cannot be formulated formally as a linear standard spectral problem. So we study, I skip boundary conditions which should be imposed in this equation, but we study quantization of energies. Okay. The question is that how to hide this H bar, which appears here. There are two ways to hide it. And so we go to from Riccati equation to Riccati-Bloch equation. If we will, what is this? Okay. So if we introduce a new variable, v, what appears here, and new function, y, what appears like this, and also make just really introduce dimensionful factor in energy, and introduce this new effective coupling constant, we arrive to equation which we called Riccati-Bloch equation. This is presented here. So very easy. No H bar appears here. This means that we hide H bar dependence. And this equation describes dynamics in quantum H bar dependent space. This is where H bar dependence is hidden in configuration space. Okay. Let's take this equation and calculate asymptotic behavior of a known function at large distances. And it's very easy to really to calculate that this is just this expansion in odd powers of v. And if we will return to original phase, what appears in Schrödinger equation, the exponential minus phase, we will have this remarkably simple expansion. Of course, this expansion is not. Interesting thing that this expansion cannot be strictly defined since the coefficients are eigenvalues and we don't know eigenvalues. So this is type of expansion with unknown coefficients, but coefficients, what appears here, have a meaning of eigenvalues. Now, to so-called, let's go to so-called generalized Bloch equation. We introduce another change of variables. We introduce variable which is G coupling constant multiplied by coordinate. This is just a new function, and this again the same change of energy. The same effective coupling constant. We arrive to this equation. We call this equation generalized Bloch equation. Let me pay your attention. Potential, what appears here, has no parameter dependence anymore. This is the parameter in original potential, which appears equals to 1. But the coupling constant, this effective coupling constant, appears in front of the first derivative. So it means that it plays a role of H bar, but it's not H bar. And also this coupling constant square appears in front of the eigenvalue we are looking for. So the meaning of this equation that we will study dynamics in so-called classical H-independent coordinate, which is G multiplied by X. Let me emphasize the importance of such classical coordinate. This classical coordinate exists only if coupling constant, if interaction is non-zero. And this is a remarkable change of variables. It's a remarkable coordinate. And when Young and Mills introduced their so-called Young-Mills theory, this gauge theory, they wrote, they paid attention that if you introduce this coordinate, these classical coordinates there, but where instead of X you put quantum field, surprisingly, dependence on coupling constant disappear from the action, And the coupling constant appears as a multiplicative factor in front of the action. So it would be 1 over g squared. This is the observation. Surprisingly, similar observation can be done in simple quantum mechanics. So if we take this equation, what presented here, we can develop perturbation theory in lambda. It's not a big deal, but this perturbation theory is presented here. So the energy, the eigenvalue, is still given by Taylor expansion, but in lambda. So this is just exactly as for Riccati-Bloch equation. But the new function we are looking for has extremely unusual expansion. And the first term in this expansion, we can immediately recognize that this is nothing but classical action for harmonic oscillator, but for energy equals to 0. And then Z1, this is correction to the classical action. So this is, we understand, this is nothing but true semi-classical expansion. Semi-classical expansion, it's expansion in powers of h bar. This is just realized here. Since those coefficient functions, the n, they have no h bar dependence in whatever sense. But lambdas, they depend on h bar, since lambda is effective coupling constant. And the incredible conclusion can be drawn out of this, that expansions in coupling constant and expansion in h bar is the same expansion, since lambda is just a combination of h bar and g. And if we take this equation, what's written here, and calculate how these solutions look like, and in already x space, so we just return from y or from z to x, and we will see that this expansion corresponds to expansion at large x, as it should be. This is semi-classical expansion. And this expansion has this extremely simple form, etc. Etc. Means that the terms which are not written here, they are decaying at large x. But the first three terms appear here. They're universal. They have no dependence on eigenvalue. And correspondingly, this expansion is the same for any eigenfunction on the level of first three terms. Okay, we can, of course, extract from this expansion semi-classical expansion, which is asymptotic at large x, and this is presented here. This term x cube of the type of its standard leading WKB correction at large distances in phase. And then there is the correction to semi-classical expansion, and there is a logarithmic correction. And this is a remarkable observation that the logarithmic correction has no dependence on coupling constant. And those first two terms don't depend on the state we study. But logarithmic term, what appears here, depends on state we study, since n is the quantum number and p is the parity. And furthermore, those three terms in this expansion, as I mentioned, they just really universal in the sense that those terms appear for any eigenstate we study. Now we make those two expansions. Let me just show this expansion at small x. Take this expansion at large x. Understand that expansion at large x is originated from expansion of those terms, what appears here, and try to match them to a single function. It took time, but since problem is very well defined, perhaps I should mention what does it mean matching. Matching means that we want to construct function which has a correct expansion at small x and correct expansion at large x. This is it. This we will arrive to this function what appears here. This function, if b, parameter b here equals to 0, this is just the first functions which were written in 2005 and 2010, but later on we discovered that it's very important to have this b. Pn, which depends on parity of x squared, this is the polynomial, non-orthogonal orthogonal polynomial, but of course those functions are made orthogonal. Since those polynomial non-orthogonal, since in a sense that the weight factor, weight function, depends on quantum numbers, on n and p. And of course, there are two free parameters what appear here, a and b. This is it. And so this is it. And then once we have this function, the question is that how to define those parameters a and b variationally. And if we define those parameters variationally, we can calculate variational energy with this function as a trial function. We can discover immediately that this function gives us accuracy 10 in power minus 10, means 10 significant digits for any coupling constant. And for energy, this function is accurate in a sense that this function is locally accurate. So this is uniform approximation of exact unknown function. And the deviation is 10 to minus 6. So in any point in X space for fixed G, the function presented here approximate exact eigenfunctions with accuracy 10 to minus 6. Surprising thing that in order to get this accuracy, just 1 second, let me see how much time I have. Okay. In order to get this, those unprecedented, let me emphasize, accuracies with two parametric trial function, it's unprecedented accuracy from the point of description variational calculus. But in order to get this accuracy, those parameters a and b, it's enough to define those parameters a and b with accuracy for significant digits. If we add more significant digits to a and b, it will appear contribution beyond of those 10 significant digits in energy, which is not important for us. This result was checked numerically with a so-called Lagrange mesh method. Lagrange mesh method, this is generalization of Gauss quadratures, but to ordinary differential equations. It's extremely powerful method, developed and invented. This method corresponds to a situation when we have differential equations and project this to the nonlinear, non-uniform lattice. And the lattice points are given by zeros of classical orthogonal polynomials. This is the meaning of Lagrange mesh method. It was invented by Daniel Bay in Brussels many years ago. Daniel Bay is just an important figure in nuclear physics. So it was checked for coupling constants 0, 1, 1, 10, 20, and 100 for different quantum states. So the problem of quartic and harmonic oscillator is solved with accuracy in energy 10 significant digits and with accuracy in eigenvalue, so uniform approximation of eigenfunctions with 6 significant digits in any point in a real X space. This is just how those two parameters, what appear, behave depending on coupling constant G for different states. The definition of the state is just first number, it's quantum number, and the second number, it's parity. And the parity, we know that has two quantum numbers, is 0 and 1. So this is very nicely looking, smooth functions, and here and here. This is another interesting plot. It seemed to me this is the plot how nodes depend on coupling constant for different states. So this is just very smooth and slow dependence with changing coupling constant. Then the natural question is, since we solved this problem, we can just move ahead and say, why not to go to sextic enharmonic oscillator, which is presented here. So we have enharmonicity x to the 4 and x to the 6. More or less following the same strategy. So matching expansion of phase of y at small x with expansion, with semi-classical expansion at large x, we can arrive to this function, which does not look simple, but it does not look also complicated. And this is 4 parametric functions. So we have 4 parameters which are variational A, B, C, D, let me pay attention that we have pretty non-trivial prefactors to this exponential factor. This actually, in the language of saddle point method, shows that we can make sense to this exponential as classical action, but what appears in prefactor has a meaning of determinant. So, and this indicates that there are several saddle point methods. Saddle points. Amazingly, if you will again take this and make variational study, you will find the same accuracy 10 to minus 10 in energy of any state you study. So we find eigenvalue with this function with accuracy 10 significant digits. And the same 10 to minus 6, so 6 significant digits in eigenfunction, in any eigenfunction we study. We didn't study all eigenfunctions, but 6 significant digits in any point of real X space. Okay? But then we can just go further and say, what about general enharmonic oscillator? So we can write this general potential. And surprisingly, it can be written that there exists approximate eigenfunction for kth excited state, which can be written in such a form. So it's a generic expression. So the constant plus potential, original potential, but with parameters, not parameters which are written in original potential. Those parameters are variational parameters divided by square root. It's very important, square root. Origin of this square root is completely unclear. And I consulted with, let me say, people with in mathematics with the greatest possible fantasy, no idea from where this square root comes from, but it appears always, this square root what appears here. So we should take this original potential, extract x squared term, and we have this expression here with, again, some parameters instead of A0, A1, A2, which should be defined variationally. We have a certain prefactor, and the prefactor always defined by those two, matching those two expansions, and this prefactor is depends on potential we consider. and multiply by polynomial, which carries information about the nodes. So this polynomial contains real roots which have a meaning of nodes of the corresponding function. Now, unfortunately, this gentleman, Sorin, is not here, but he would definitely love it. This is quartic double well potential. This is the problem which attracted attention of many people. And thanks to this potential, we exist. And thanks to this potential, Peter Higgs got Nobel Prize and predicted Higgs boson. So this is the potential. So it's two identical wells. This means that there exists a symmetry x to minus 6, x to minus x, Z2 symmetry, with respect to the peak or tip of the barrier. And this is the function, which again, difference, surprisingly, difference with functions I showed appears in the factor what appears here. So the exponential term should be multiplied by a factor which depends on parity of the states we consider. In the positive parity states, since this potential there exists, since symmetric, there is a parity, we should multiply this by cos with two parameters and this by sinh with, again, parameters here. And this is more or less it. So this function, we can count how many free parameters here, but not many of them, very few. And parameters of the polynomials what appear here are fixed following the orthogonality condition to the all states, Sturm theorem. And this function is supposed to give accuracy in energy 10 to minus 10 for any positive coupling constant G, which should be extremely impressive for people who study exponential tunneling. So we describe tunneling energy gaps with accuracy 10 significant digits for any G. And also in an eigenvalue, in eigenfunctions, we have a little bit loss of accuracy here. So we predict from 4 to 6 significant digits locally in eigenfunctions. But then perhaps in order to finish, I would say that all those formulas I showed you, they just provide unprecedented accuracies in both eigenvalues and eigenfunctions. All those functions presented here are in contradiction with extremely well-established, famous Lazarus-Fuchs theorem. It's 19th century. Fuchs theorem tells you that if potential is polynomial, eigenfunctions should be entire functions. But we have singularities. This means that in spite of the breaking with those approximations of Fuchs theorem, we're still able to reach incredible accuracies in eigenvalues and eigenfunctions. This means that existence of those singularities in approximants don't really break effectively Fuchs theorem. It's just they only tell you that the Fuchs theorem holds up to accuracy what we present here. And of course, if we will want to go beyond of this accuracy, get more accurate results, we should really modify those approximations. But the question is, do we need to do it or not? We already got accuracies which are more than sufficient for any physics applications. And the last slide, I'm just surprisingly almost on time. Yes. Last slide is acknowledgement. Since I studied this problem of anharmonic oscillator all my life, since young years. And there were people who, and many times I try to give up and say that I'm not able to solve this problem. It's necessary to be honest to yourself that, okay, it's much more than before Juan Carlos showed up. Kermar Tirasyan, who was my teacher, one of the most beloved disciples by Landau, he was responsible in Landau School for Nuclear Physics. Two mathematicians, I'm sure that you know those names, Felix Alexandrovich Berezin, mastermind of supermathematics, who somehow, till his departure, talked to me sometimes trying to explain that this problem is extremely important from mathematics perspective. Misha Shubin, lifelong friend for my life, and who also just pushed me and said, don't give up. And he also used to say publicly that mathematics behind of this simple anharmonic oscillator is so complicated that he thinks that today's contemporary mathematics is not able to treat those problems adequately. It's his words, public words. Zeldovich and Vitaly Lazarovich Ginsburg, who also here future Nobel Prize winner, fortunately he is not with us anymore, who always said that this problem of such importance that it's important to continue, not to give up. Thank you very much.
So many thanks for this nice talk. So any question, remark?
Yeah, I have two questions, but let me start with the first. There's, of course, the WKB theory to making an expansion, and in the WKB theory, there are these turning points for the energy, and then there's a technique to get the eigenvalue expansion to very high accuracy in the semi-classical limit. Can you see this popping up in your in the limits you study, or yeah?
Of course.
Yeah.
But writing this semi-classical expansion, we never ever approach the turning points. We are far away. We are deeply in quantum domain, in beyond of classical domain. Therefore, in principle, we should forget about the existence of turning points. But once you make matching, it immediately restores you turning point.
Yes. Yes.
It immediately. But again, this is one of the, sorry to say, it's one of the mysteries of all these considerations. Simple matching provides you turning point and semi-classical approximation around turning points.
And another question I have is, when you look at your approximate wave function, let's say for the quartic harmonic oscillator, maybe you can go back to this formula for psi NP. You had it. Yeah, this one. It is reminiscent of the form of the harmonic oscillator. There's the exponential function is, so to say, the ground state, the vacuum function, and then these the Pn, the polynomials, are reminiscence of the Hermite polynomials that appear when you yeah. So is there something like a creation and annihilation operator that you could that produces these polynomials when you apply it to this vacuum vector? I mean, like in the spirit of the harmonic oscillator?
Not up to my knowledge. You know, and I don't think such creation and annihilation operators exist, but there are definitely mathematics abstraction for existence of such. It's not just they exist, but we didn't find them. There are mathematics abstraction to that. and of course related with corresponding Heisenberg algebra, etc.
Okay.
So you mentioned that originally you was motivated by the lambda 5-4 theory, and now you solve the problem, and it's with a very impressive accuracy. Can you comment about the impact that this could have in the lambda 5-4 theory?
Thank you very much for this question. Of course, since motivation was by field theory, that immediately we can say, listen, we have so simple, so nice formulas, maybe we can project them to true four-dimensional quantum field theory. No. And the reason is that actually this is the problem with what Dirac actually dealt with and how he invented his Dirac equation. We deal with square roots. Nobody knows in quantum field theory how to deal with once a square roots of the field shows up. So in principle, generalization is just straightforward. Replace x by phi, but you cannot replace x by phi. You should replace x squared by integral of phi squared, which looks like as a free term, and etc. But we don't know how to treat it, this square root, except in perturbation theory at small x. But we don't know how to go, how to, this, I would say, this is the problem for next generation. How to deal with, I would say that all field theory we have experience with, just field theories with, let me say, polynomial in fields, Lagrangians. But we never, at most people try to use, let me say, interactive Lagrangians for exponential of phi. This is, it reflects the Toda model in quantum mechanics, many-body quantum mechanics. But in field theory, this is completely open field, and unfortunately all classics of quantum field theory who could somehow think in this direction, like Weitmann or Haag, they are gone. And you have nobody to ask how to move in this direction. What do they think following their appearance? But the question is absolutely valid and absolutely correct.
Any other question? Yeah.
It's a curious question. In classical mechanics, we know that the enharmonic oscillator have this property that if the energy grows, the frequency change, and this gives a very strong stability for the nonlinear system. In that case, there are something equivalent that if the energy change, the values change in that form that give some kind of stability.
I would say this is not a question to me. It's a question to quantization, this, I don't know, Bohr-Sommerfeld or whatever, how to quantize. Since you know, in classical mechanics, all trajectories we study here, they are periodic. But if harmonicity appears, they are still periodic, but the dependence on amplitudes appear in corresponding, if you calculate the frequency. The frequency is not constant anymore. Frequency should have absolutely non-trivial dependence on coupling constant. And this, of course, was observed by Jacobi. This, of course, Jacobi function contains all this information. But the question is that they're so complicated with these simple Jacobi functions for x to the 4 potential. And to talk about stability, again, before talking about stability, you should explain to yourself why quantization choose only a certain periodic trajectories, not all. What happened with all trajectories, periodic trajectories, which just should disappear in quantization? Is it more or less what you wanted to ask?
Curiosity that I wanted to see about this equivalence of the classical and quantum. For example, the camp theory depends very strong for this property. And I don't know if we want to create a camp theory in quantum mechanics, if we need something equivalent of this property.
It's a proposal for next generation. This is for sure. This is not a question which can be answered like this. Just quantum analog of camp theory. And again, one of the authors, famous authors of camp theory, Arnold, is gone, and but he knew in classical mechanics and quantum mechanics as well. He could answer this somehow, what he thinks about that, but I have no.
Yeah, I think we should stop the discussion right now. Should move on to the next talk, let's say in 2 minutes or something like that, with Sebastian Bateau.